Hello, and welcome. Um, Today I am dressed as surfer dude, college douche bro, and that's because we're officially starting waves as opposed to just the simple harmonic motion stuff. So that's exciting. Now, you might notice I have this lovely, lovely backdrop. I thought that it would look pretty cool. I might be able to do some things. I think it does look cleaner that you don't see just like everything behind me, but what you might be thinking is, yo, Mr. Foster's got a green screen. This is gonna be dope. And while I was also hoping that would work, here's what happened. This isn't working. Obviously, didn't quite work out very well, but hopefully we can get it working in the future. Maybe, I don't know, there'd be another investment for me, like the lighting and stuff, and we'd need a new sheet or whatever, so we'll see. But for now, let's get started with waves. So you'll notice the first thing is just the definition of a wave. We think of lots of things when we think of waves. The ocean, obviously, or sound we know comes in waves. Light, even maybe, is in waves, although light is a little bit of a different kind that we're not really looking at. But a wave simply is an oscillation that carries energy from one place to another, and that'll serve as like our base definition. But what's really more important for right now is that waves come in a few forms. Waves come in two forms specifically, and we're going to have to go to the lab to show you what those look like. So I'll meet you there. Alright, welcome back to the lab. So, I came here to show you the difference between transverse and longitudinal waves. So, I have this lovely slinky here to show us the difference. So, let's check it out. We'll start with transverse first. So, a transverse wave is a wave in which the energy of a particle moves perpendicular to the motion of the particles, which sounds really, really confusing. So, let's look at an example. So the slinky is really good. It'll help us show both kinds of waves. So a transverse wave is actually the shape of wave that you're usually used to seeing when you think of a wave, right? The loopy, swoopy shape. So a transverse wave looks like this. So which way am I moving the slinky, right? I'm going this way, to my left and right, right? Which way is the energy traveling? It's traveling from me that way, off screen, right? So the energy is traveling this way, but take a look at the slinky, right? The slinky is actually, energy is going this way, but the slinky is actually itself, at any given point, is moving this way, right? This direction might be a little hard to see, but let's take a look at this simulation from our friend fet.colorado.edu. So on this simulation, you can see waves on a string, it's vertical. So take a look at the actual individual beads as they move. So you can see the wave is going from the oscillator out the little window, right? The energy is moving from left to right across your screen, right? But take a look at those green individual beads on the string, right? The beads are moving up and down, right? The wave's moving left to right, but the beads are actually moving up and down. And left and right and up and down are perpendicular to each other, right? The wave is going this way, but the particles are going this way. So perpendicular, transverse wave, the shape of the wave that you're used to seeing, right? So now, longitudinal, the other wave. We can actually show that with the slinky as well. So before I was moving it this way, right, and the energy was going this way. But a longitudinal wave is a wave in which the energy travels parallel to the motion of the particles. So our goal is to get the energy and the particles going in the same direction. So instead of moving it like this, I'll actually be bunching it up and releasing. One more time. I bunch up and I release. So which way is the energy going? That way still, right? It's going from me, I bunch up here, and then it travels that way. But which way is the slinky particle moving, right? They're moving back and forth. You can see it shaking this way, right? So if I release it, the energy is going that way. And the actual slinky bits are moving that way as well. So it's a longitudinal wave. They're parallel to each other. Again, we've got a simulation to look at this one, also on FET. It's actually of sound waves, because sound waves are a really, really good example of longitudinal waves. You can see, as I press the green button there on the simulation, that the whatever speaker thing is oscillating, it's bouncing back and forth, and it's sending vibrations out into the airwaves. Those particles there are the airwaves, but you can see that the waves are traveling right from the oscillator out across the screen, right? It's traveling away from the speaker, which makes sense, right? The sound is going out and away. But notice those little bitty particles are actually supposed to be air molecules moving. And you'll notice that the air molecules are moving back and forth as well, right? So they're going in the same direction. They're going parallel to the energy. So it's a longitudinal wave. Longitudinal, waves and energy go in the same direction. A transverse, they go perpendicular to one another, right? There's the regular shape, and then that we think of a wave, transverse, and then there's longitudinal, which goes back and forth. I hope that makes a little bit more sense. We'll go back out of the lab. See you later. All right. I hope you learned a little bit more about transverse versus longitudinal waves. But to really talk more about waves, we're going to have to learn about the wave parts a little bit more. You've got this little diagram right here on your sheet, right? And we're going to be filling that out to learn more about the parts of waves. So that first blank there, in fact, we'll talk about the first two because I think they're kind of straightforward. So that first one you see is called a crest, right? The peak of a wave, the top is called the crest. I feel like that makes sense. If you've been to the ocean, you might see that they talk about the crests of the waves, meaning how the wave crests, the top sort of rolls over. It's the top of the wave, crest, right? That kind of makes sense. And in the bottom, that next slot that you're seeing is the bottom of the wave. It's called the trough. I feel like that makes sense too, right? Trough, or those things that you usually see the words for, like an animal eating out of a food trough, but it kind of looks like the same shape, right? Trough is the bottom. I feel like that visually makes sense on the transverse wave that you're seeing, the shape that we're used to, but might look a little bit confusing on the longitudinal wave, rather, is the word I was looking for. So see that the crest on the transverse wave, the top of the peak, lines up with the part where the particles are really pushed together. And it's sort of like, you can think of it like the high energy portion of the transverse wave, the part that's above that middle line there, corresponds to the high clump on the longitudinal wave, and that's how you kind of distinguish. See, and then there's the trough portion, right? That bottom part on the transverse wave corresponds to the relatively empty part, like the not compressed, the very open part on the longitudinal wave. And that's sort of how those match up. There's the high point, or the high concentration, and then there's the low point, which has the lower concentration of particles. And that's how those line up. But there's also another reason that it's kind of a weird comparison to call these the crests versus these the troughs. Because we actually there's crest and trough work for both cases, but there's actually more specific words that you might hear used with longitudinal waves, where what we're calling the crest, or the concentrated portion, is actually called a compression. And the trough, or the spread out portion, is actually called a rarefaction. But I feel like those words are a little bit confusing. Compression makes sense, but rarefaction, like what? So I think I'll be using crest and trough a little bit more, or describing the particles themselves as we talk about those. But for now, crest and trough, or what we're calling both of those things that you've got labeled there on that diagram. Which brings us to the next point, which is actually given that middle line on the transverse wave. Notice that it doesn't really correlate to anything on the longitudinal wave, because there's not as an obvious like a point for this. But what that line right there in the middle is called is the rest position, right? So the rest position is just, imagine when I was doing the slinky, right, I was moving it up and down. It was oscillating, but if I was just holding it at rest, right, it would just be that straight middle line there. So it's the rest position. It's the middle point, right? That makes kind of sense. That's pretty straightforward. Pretty not complicated, I think. But that rest position serves us really well when talking about our next blank. I'm going to skip over D and go to E, actually. Our next blank is that part that looks like it's measuring from the rest position to the crest, right? And what that's called is the amplitude. Amplitude is simply the height of the wave. I think this is catchy. It's from rest to crest, right? It's the height of the wave from rest to crest. That's what amplitude is. Now you could also go from the rest to the trough. That should be the same height, right? They're the same distance from the rest position. But I think that rest to crest sounds cooler. So we'll be mainly using that, rest to crest, as our amplitude. Amplitude, height of the wave, it also has to do with the energy that the waves carry. Remember, waves carry energy from one portion to another, or from one place to another, and the more amplitude, the higher energy. We'll talk about that a little bit more when we look at when we look at our next section, which is going to be a more specific look at sound, actually. But amplitude, height of the wave, also connects to energy. More amplitude, more energy. But that brings us to our last one, which is the slot letter D, and D it's measuring to a width, right? It's got 2 marks, and it's that line in the middle. So what that is, notice that it connects one full oscillation, one full up and down, and that is the length of one oscillation, the length of one wave, aka it's the wavelength, right? The wavelength is just the length of a wave. You can either measure from crest to crest or trough to trough. Those are the easiest ones to do. You can measure from 2 spots on the rest position, right? But you need to make sure you skip one, because if you don't skip one, you're only getting half of a wavelength as opposed to the full up and down. If you just measure one across, you're either getting just one bottom part or one top part and not getting the full oscillation, one full back and forth. So make sure that if you were measuring wavelength via the rest positions, that it's every other one is one full up and down, right? If that makes sense. And so those are our basic definitions. I feel like those make sense, right? Crest, trough, rest position, amplitude, and wavelength. Those are pretty basic definitions. But feel free to. I think the diagram is a really great indicator of that. But I feel like they mostly make sense in terms of the transverse wave, not the longitudinal wave, right? We see that for wavelength, the wavelength of a longitudinal wave is from those concentrated points, from crest to crest. Still, you can still do the same thing, trough to trough. But I want to look a little bit closer at how longitudinal waves actually relate to sound. Sound is a longitudinal wave, right? So I showed you the demonstration before that had those connections before, but let's take another look at it really quickly so that I can talk a little bit more about what amplitude and what wavelength look like in terms of sound. Alright, so we're back at the sound simulation. I showed you this earlier just to show you how you could see that the waves were moving in the same direction as the energy is going, right? That the particles are moving in the same direction that the energy is going, right? They're going from left to right on your screen. The particles and the waves are moving from left to right to your screen. Sound waves, great example of longitudinal waves. But you may have noticed that there's these frequency and amplitude sliders over here, right? And so I wanted to show you what happens when you mess with frequency and the amplitude. So frequency, a topic that we talked about previously with simple harmonic motion, right? Frequency was the number of oscillations or the number of events per second, right? So if we crank up the frequency, we should see more waves per second, right? Higher frequency, more waves. I think that should be familiar somewhat, talking about that in a previous class. So amplitude, though, might not be as obvious. Let's see what happens when I crank up the amplitude slider. Notice how clumped up these waves are first before I crank up the amplitude slider all the way up to max. So notice how the waves here look more clumped up, right? Those clumps are bigger, they're denser, and that's kind of what amplitude means for that, right? You're not increasing the height of the spring like I could with the slinky. What you're doing is you're making the clumps larger. So that's what happens when you touch the amplitude slider, but let's see what happens when I touch the frequency slider. So it's at minimum right now, right? We're at the low frequency, meaning few waves per second. But if we crank up the frequency slider all the way up, notice how there's more waves, right? The waves are coming out faster, and the wavelength, remember the length between waves or the length of a wave for longitudinal wave was the clump to clumped. So these clumps are closer together than if I crank it all the way back down to minimum. See? Let it reset a little bit. Yeah, see, here's a wave and there's a wave. Those are much further apart than they were before. The wavelength is longer here because there's fewer waves per second, right? So frequency and wavelength are kind of related. Higher frequency waves have shorter wavelengths because the waves are closer together, right? I feel like that makes sense. But there's one more part to this that I wanted to show you guys. I'm going to crank the amplitude back down for a second to the middle. So there's also this portion on this that says play tone. This is sound after all, right? Sound, we hear sounds. Sounds have different volumes. They have different pitches, right? High pitch, low pitch. And so frequency and amplitude are actually how sounds have different volume and have different pitches. So let's see what happens when I hit the play tone button. My mouse isn't cooperating. Sometimes they just die. Alright, so if I hit play tone, this is my low frequency, right, sound. Crank that up a little bit. So, watch what happens when I touch the amplitude slider. It gets louder, right? Remember how I said a amplitude is the height of the wave or the energy that it carries? Well, it turns out that a higher amplitude means that the sound is louder. I feel like that makes sense, right? More energy means it's louder. It's the sound's hitting your eardrum, right? So if it hits it harder, it's louder. So let's see what happens when we increase the frequency, right? The waves will get closer together. The wavelength will be shorter. Let's see what happens if I adjust frequency. We're going to turn down the amplitude a little bit. So yeah, high frequency waves. I'm going to stop there. High frequency waves are higher pitched. You're hearing more waves per second. That's what makes the pitch of a sound go up, is that there are higher frequency waves. So yeah, that's pretty neat. And those were kind of the main topics that we wanted to talk about today. We wanted to talk about just the two main types of waves that we're looking at, or the two varieties that waves come in, like this, and a little bit of a look at how amplitude and frequency relate to sound, right? Higher the amplitude means the louder the sound is, higher the frequency means higher the pitch, right? The low frequency was a low pitch, high frequency was a high pitch. Let's not do that again. But yeah, that's kind of all that we're looking at today. We'll look a little bit deeper into these in the next lesson. But I hope you enjoyed that, which was this nonsense today. Catch you later. Oh, hiccup right at the end. Dang.